I'm ready when you are. Okay, good. Okay, welcome to your first science-ish lecture of the class. Probably the only one you're going to get from me. I will apologize in advance. It's a bit of an old man history lesson, which I know isn't super exciting per se. But that said, you will, as you encounter data problems over the week, probably have questions as to why things are the way they are. And a lot of that ties back to how the mission came about and the evolution and the design choices. So don't view this as a history lesson, view as it more of here's the background you might need to understand what you're going to be looking at the rest of the week. So through that, basically going to compress 23-ish years into a little less than a half an hour and then take questions. I say it's 23 years because it literally was. The idea of PACE is old enough to legally drink here. It might be older than a few of you, frankly. It really was initiated not long after CWIFS launched in 1997 and MODIS Terra launched in 1999. The reason for that is they were really groundbreaking missions. Before that, there wasn't ocean color from space on global scales. And because they were successful, the community and some senior leaders were like, well, great, if we had to do this again, what does that look like? Where do we go from here? And in any agency life cycle, it takes a really long time to go from an idea to actually getting the funding to go and build something. So the idea of PACE really came around when you didn't have the consumers market that you have today. Like right now, I wish I were a student because at your fingertips are so many different kinds of remote sensing assets and autonomous vehicles. That doesn't exist when this all starts. So how does something like this come around? Well, it's a lot of writing, it's a lot of research and white papers. There was a Carbon program that actually had a beautiful, beautiful plan for how NASA would conduct research for the next 20 years. It was getting ready to be funded. It came out in summer of 2021, and then September 11th happened, and everything changed in terms of priorities, and US and abroad. And programs like this got shut down. So, as you probably have heard, the Decadal Survey kind of dictates how a lot of US missions, especially at NASA, go forward. The 2007 Decadal Survey and this plan for NASA's ocean biology and biogeochemistry research, which was run by Paolo Bontempi at the time, were really the driving factors for a lot of the thought that went into it. And this is just an example of 4 programs where missions were formulated and ideas were created and written down and pitched to the community and headquarters. And then finally, with the Decadal in 2007, there were a number of missions that were created on paper for production, let's say. And the important one for PACE is ACE, Aerosols, Clouds, and Ecosystems mission. They even had their own science team that did some concept studies and so forth that initiated what this would be. And frankly, it was really ambitious. If you've heard of AOS now or ANCCP a couple of years ago, which is a previous branding of this, effectively, it's been 15 years since that mission's idea came about. Why it's important for PACE is not just because it's most of the acronym, but because there was supposed to be a 4-instrument observatory, have a radar, a LiDAR, and an ocean radiometer, which is, again, ambitious to put four instruments on one platform. What ended up happening is about halfway through that decade from the Decadal Survey in 2007 to 2017 is headquarters decided to split that observatory up. And they realized that polarimetry and ocean radiometry were far more advanced in terms of being able to be built quickly than the LiDAR and the radar that they were looking for. So they split, and there was this climate program and document that came out that basically said, go and build pre-ACE, which was the genesis of PACE. So rapidly responding to that, there was a science definition team formed. Again, it's not a real mission yet, but in 2011 and 2012, 40 of us sat down and page documents you've read to prepare for this class. We even had a science team before we had a real mission. We're blessed now that we're on our 3rd science team, but there was one that was formed in early 2014. And it was really great because it got everybody's juices flowing in terms of thinking about how oceans and atmospheres work together. But it wasn't until the end of 2014 where there was a letter of direction from headquarters that said, okay, PACE is a real thing, go out and build it. And it was at that time we changed the pre to plankton. So now we're plankton ACE. So yeah, that was December of 2014. In 2015, they started assembling the team. This is all mostly based out of Goddard, NASA Goddard, so about 25 miles south of here. And I had the pleasure of starting in February of that year, and you have all been stuck with me ever since. So why? Why invest in a mission like this? We're just shy of $1 billion, which isn't super expensive in the grand scheme of flight projects, but that's still a lot of taxpayer money. These basically represent that. Why you are here, what I hope you're interested in. This is a visualization of 4 different phytoplankton communities and their evolution in space and time. This is similar, but it's for atmospheric aerosols. And for the oceanographers out there who aren't familiar with a lot of atmosphere work, an atmospheric aerosol is anything in the atmosphere that isn't a gas. Clouds are a special form of that. We treat them differently because they're clouds, but it's basically anything else that isn't a gas. These are models. They're beautiful. They're amazing. We have no ability to create this with direct observation from space on global scales until you launch PACE. And so this is why you are here, is to take, and this is what I'm hoping you're building your career on is, hey, this model's fabulous. I'm going to do it with real data. Now, in this case, I say real data. We still have the whole atmospheric correction problem, and there's a shit ton of modeling in it, but nevertheless, it's an observation from space. And where PACE fits in is it's observatory, the fact that there are instruments that can do both, and 2, that it is global. So there are other hyperspectral instruments in space. They're fabulous. Their repeatability is an order of like 2 weeks. I'm defining global as you see the entire globe every day. Just because water moves, right? So if what you're looking for today isn't observed, it might not be there tomorrow. So just so you know, we're not minimizing other missions, just that this is the first chance you all have had to do truly global research. So that's 2015 when that all starts. We're going to fast forward 9 years. This is mostly just for your amusement, but during those 9 years, we had a 34-day government shutdown. We were canceled 4 times by the White House. I'll just let you imagine what 4 years those were. We've had multiple community science, which have been really rewarding. There's been a lot of leadership changes, and so for the new bosses, it's always a good time. They levied a ton of new requirements on us, and then you might ask yourself, well, if you live in the cloud and the satellite data is coming down, housekeeping on S-band, and I know this is NASA jargon, but you're getting science data on K-band, why isn't it all together? Why do you have to repackage it? Requirements levied by the agency for new technology development and things like that. HARP-2 team, we had a broken prism, so that was a tough month, but they recovered. And then there was that whole global pandemic that shut us down fully for 4.5 months, and then basically had ramping in. And many of our jobs became salesmanship to keep this going forward when you have to tell leadership, why are you 4.5 months behind? Because we couldn't go to work for 4.5 months. You can't build a satellite if you can't touch the metal. So, sorry, whining. But here we go.
2, 1, ignition, engine full power, and liftoff of Falcon 9 carrying NASA PACE. Go Falcon, go NASA LSP.
I put this in for 3 reasons. 1, it allows me to take a drink and be calm. 2, when I think about launch, I still choke up. And 3, there's a moment here that is so cool. It is, many of you don't have children, but like when you leave your daughter at kindergarten for the first time, or you drop off your son at college for the first time, I had a moment. Come on. Aw. Oh, there we go. These were butt clench moments, like, oh my God, please release. And the worst part is after separation, it's a half an hour before you know if the power gets turned on. So you're sitting there not knowing, seeing anything, waiting. It's this. Last time anybody's laid eyes on her. See, already choked up. Okay, but here we are. That was February 8th, really early morning. It is exactly day 178. So like I was saying before, you're in pretty early, which is really remarkable. So the timing of this for us couldn't be better. Okay, so getting to the mission, and some familiarity with what the instruments that you will be working with look like. And I'm sure most of you know this, but I just want to make sure you know you have a resource in case you forget. We already talked about the science. The legacies, which are, I listed mostly NASA ones here, are ocean, atmosphere, and cloud science from these multispectral radiometers, but then we have multi-angle and polarization capabilities from MISR and Polder as well. Key characteristics. I've already told you how long it took to get there. You're going to hear things like it's a 3-year design life. I don't want you to be worried that it's a 3-year mission. That is just an engineering term for redundancy, parts quality, and so forth. There's somewhere between 15 and 20 years of propellant. So as long as everything's working, we can be a multi-decadal system. To their credit, SpaceX is a lot of things. They inserted us into the perfect orbit. We didn't burn any extra propellant, and that actually extends the mission for like 5 to 10 years, which is really, really cool. Altitude is just shy of 700 kilometers. We're polar ascending. I'll show you. No, I probably won't show you a video of that. Anyway, what that basically means is you're coming up over the South Pole to the North Pole. It takes roughly 90 minutes to make that orbit. It does 14 and a half orbits a day. It has wide swath on 2 of the instruments, which is why we can paint the entire globe. So 1 o'clock today, as you're walking back from lunch, you can look up and wave because it sees roughly every piece of real estate at the same time every day, and that's what sun synchronous means. Okay, so 3-instrument observatory. We'll walk through that really quickly. Primary instrument is Ocean Color. It's a stupid name. I'm really sorry. The Ocean Color instrument is not clever, especially since it's capable for terrestrial applications, and it's really remarkable for aerosol retrievals, and it's okay for clouds. So we call it Ocean Color, but it's much, much more than that. That is the only mission that was required all along. We're very, very blessed to have 2 contributed instruments that were optional, which had its own series of headaches because they're not in your requirements. The first is SPEX-1, which is from a consortium of organizations in the Netherlands. And the second is HARP-2, which is from this place you are sitting in now. They are, for context, much smaller. We'll show you that. But they are mighty, and they play really well together. And all of this is being run out of mission control at NASA Goddard, again, down the road a little bit. Okay, so Ocean Color instrument. The name does make sense when you think about performance. The ocean is so much darker than any other target. But now we have a requirement for a super dark ocean, and then you have middle brightness aerosols, and you have super bright lands and clouds. Building something that has a dynamic range that goes from dark to bright on the same instrument is much harder than I'm making it sound like. And since the hardest part is doing the dark retrievals, Ocean Color really defined what this instrument is all about, and the other disciplines get performance for free. So what's important here is that for the first time in a MODIS VIIRS kind of ecosystem, we are continuous resolution from the ultraviolet all the way into the near infrared. We've never had that hyperspectral nature before. One thing you will notice when you play with the data is that even though I'm telling you the requirement is down to 340, we actually shine light on detectors that go down to 320. So it goes much, much farther into the ultraviolet than we were originally planning. This is entirely serendipitous. The way it's basically a 2 spectrograph system that overlaps, that runs from 320 to like 605 and then 595 to 890. Because of the size of the spectrograph, we got that ultraviolet light for free. So there is no heroism that went into calibrating anything shorter than 340, but the data are there. So it is something that maybe you can think about playing with. It's valuable. There's a lot of science you can do down there, but you need to treat it with kid gloves. And because the performance isn't as, maybe you start thinking about ways of doing spatial aggregation rather than using 1 pixel. If you did 9 pixels, then suddenly your performance starts to increase, at least from a noise level. One other thing that's important about this is that it is mostly 2.5 nanometer steps across that full range. I say mostly because right now there are two parts of the spectrum where it's 1.25 nanometers, and that's chlorophyll fluorescence and oxygen A and B absorption bands. So you'll notice, while I say it's continuous 2.5, there are little places it's not. Throughout all of that, the bandwidth is 5 nanometers. So it's a sliding 5 nanometer spectral resolution system through all of it. One real neat thing about this system is that we can configure the placement of those 1.25 nanometer steps orbit by orbit. We're not doing that now, but sometime when we learn to fly it a little bit better, if there are interesting science questions or something we're trying to respond to, that's when maybe you reach out to us and say, hey, there's something really remarkable going on in this body of water, and hey, can we turn on a different kind of spectral resolution somewhere? We'll grow into that. 7 shortwave infrared bands listed here. 7's a little bit of a lie. There are 7 wavelengths listed here. There are low or standard and high gain bands at 1250 and 1615. That's purposeful. The standard gain is for atmospheric science. The high gain is for ocean science. It's an engineering choice. Again, I said the ocean is really, really dark, but you want to use shortwave infrared bands for atmospheric correction in some places. If you've ever had the MODIS or VIIRS experience, you've been playing with those bands, you realize they're not optimized for ocean performance. They're optimized for a bright signal. So with the high gain choices here, we've basically shrunk the dynamic range of the radiance that it can retrieve. So these are special bands that are tuned for a very low signal. The high gain will saturate over clouds and other things, but it should improve your ability to do atmospheric correction. We're a single science pixel. That is simply a way to mitigate striping. MODIS has 10, so you can always see stripes in the ocean and sometimes on land. 1 to 2 day global coverage. Ground pixel size, I say it's 1 kilometer at nadir. It's a tilting instrument, which means it's actually 1.2 kilometers fore and aft as its smallest pixel. And because it's wide swath, that pixel size will grow on the edges. We do a tilt, which I'll talk about more, and then there's calibration stuff going on as well. So 2 things that set this instrument apart from its predecessors. The first, of course, is the move to spectroscopy. This is just a cartoon that shows you where the multispectral bands for SUIS, MODIS, and VIIRS were located. We should not minimize the fact that this is multispectral, that ULCI and SGLI are as well. They're very, very intelligently placed bands. They're put in positions to separate phytoplankton signals from a background of everything else. And 40 years of great research. But now we have a continuous one, and the reason this is important is really just to have more information to be able to do spectral matching or derivative type techniques. And just as an example of that, I know a lot of you have seen this slide before if you've heard me talk. I use Arabian Sea, northern part of it, as a case study, because that's where I did some work for my PhD. There's a really profound ecosystem change that has happened over 20 years, probably longer, where it shifted from a diatom-dominated community during monsoon season into a Noctiluca dinoflagellate. And that's really changing the entire ecosystem structure for reasons we can talk about offline. The punchline is that if you look at the signal of those 2 communities, when you are only looking at VIIRS wavelengths, where you have the diatoms as black and the Noctiluca as red, there's very little new information about each one that can be used to separate these 2 communities. And so moving to this hyperspectral signal suddenly provides information content you don't have before. This is intuitive, you know all of it, but nevertheless, just in case you didn't know the pedigree, there it is, because the promise of PACE all along has really been phytoplankton community structure. Now you may ask, why tilt? This is a huge engineering challenge. It really stressed engineering and budgets, but I think you will appreciate why we do this. The punchline is that SeaWS was the last ocean color mission that ever flew. MODIS, VIIRS, all the others that don't tilt are ocean color capable. They're not ocean color instruments. Ocean color instruments avoid sun glint. That's not debate. You might want to debate it. It's not debatable. If you're looking in the sun glint, you're not ocean color. So why do we do it? Well, this pattern here is everything you would lose to sun glint in one particular orbit. When you tilt fore and aft 20 degrees, that collapses to this. And you can see it in Rio, MODIS, and CWIS data here as well. This is profound if you think about how the size of the real estate that you recover by tilting. So this is just for one season, but we did a study that talked about how fast we tilt over 20 degree, I think we were doing 20 degrees fore and aft here. And the idea is we are roughly here. We're a 30 to 60 second tilt. So we're still losing, maybe 4 million square kilometers relative to like an instantaneous tilt, which is impossible. But if you don't tilt, that number grows to 16 million kilometers. So just for context here, 17-ish million kilometers, and this is every 2 days, is roughly the size of South America. And now start thinking where tilt is. It's at the subsolar point. What happens at the subsolar point? Things like El Nino. So you're really blind to a lot of Earth system phenomena if you can't see it because of ocean color, not tilting. So saying all this because from a geometric point of view, it may present a challenge. Not every, you have extra geometry to be thinking about, but also because there are features in the data that manifest because we collect data through the tilt. And one of these, I'm sure Ivana will tell you about tomorrow. There's nothing wrong with the radiometry from OCI as you go through the tilt region. And those data are available to you. They are good radiometry, but they have sun glint contamination, which means they're not good for ocean color geophysical retrievals. And there's some funny ways in which they manifest. So saying this all as be careful. Okay. Our other instruments are the two small but mighty polarimeters. They play really well off of each other. You'll notice HARP2 is multispectral. It's got roughly it's got 4 wavelengths that are roughly positioned here, not exact, whereas SPEX1 is continuous from the ultraviolet into the near infrared in continuous 5 nanometer steps. Neither have shortwave infrared. All 4 HARP2 bands are polarized. Same is true for SPEX1, but their polarization retrievals are in a different step than their intensity. So that if you're playing with the polarimetry data, you need to be aware that the spectra don't necessarily align perfectly. HARP2 is hyperangular. It's 10 viewing angles for the blue, the green, and the near infrared, and 60 viewing angles for the red. SPEX1 is only 5 viewing angles. It's a wide swath HARP2 instrument. It's a narrow swath SPEX1 instrument. So the repeatability for HARP2 is roughly the same as OCI, whereas SPEX1 is plus or minus 30 days. So it's about a month. And you can see their spatial footprint here. But the reason they're really exciting is simply that, and I'm oversimplifying this, but by having these instruments, you can do things you can't do with the primary instrument alone. So the hyperangular nature of HARP2 is really great because you can do cloud things that you can't do with OCI alone. So we're really pushing cloud retrievals forward. It's also got a swath that officially matches OCI, which means you might, in your project, start thinking about merging HARP2 with OCI, either for atmospheric correction for some other kind of retrieval. The hyperspectral nature of SPEX1 is really remarkable. It does clouds as well, but for aerosol climate objectives. And then when you put all of this stuff together, there is more information content. You're going to get buried by it. I mean, it's 5,000 pieces of information per 5 kilometer pixel, I think, if you put everything together. It's one of the reasons you're here. I don't know how you push that much around. But it's a lot of information content, and frankly, what I'm most excited about for polarimetry in the context of all of that is doing hydrosol and ocean color retrievals from polarimetry. I think that's going to be pretty groundbreaking. And the reason you can do more with polarimetry than you can do with single intensity is one, it's multiple view angles. OCI does tilt, it's 20. In yoga, it would be coming up over the South Pole, looking behind, get to the subsolar point, and then you do 40 degrees and go forward. There's always a hot side and a cold side. But it's still single angle. I mean, you're only viewing the Earth from plus or minus 20 degrees. It's a single angle instrument. With this multiple viewing, you're seeing the same real estate from different, it would be like I see, as I'm flying over spot yoga again, it would be I'm looking at it, I'm looking at it, I'm looking at it, I'm looking at it in the level 1C files. So you have a different perspective of what that piece of real estate looks like. And then polarization is really cool too. incredibly difficult to explain. I'm not your guy for that. But nevertheless, you have polarized sunglasses, you're looking at a body of water, you tilt your head, you can see that the intensity of that light changes. And that's, light travels in two planes and circular, and that's what's being measured here. And then this is just an example of looking at intensity, which your eye would see in a parking lot at NASA Ames. And then if you're looking at the degree of linear polarization, which is just simply the ratio of linear polarization in the numerator to total intensity on the bottom, the whole world looks different. And that information is really profound for doing a lot of other different retrievals, especially in the atmosphere. Oh, I did put this in, I'm sorry. Boring. How's that going? This is just going to tie basically everything I said together, but it'll give you one more view of what the orbit is going to look like. Again, it's ascending with a 1 o'clock equatorial crossing time, which means it's roughly 1 o'clock everywhere you go. Obviously ascending here. I talk fast. One more glimpse of the characteristics of each of the instruments. In case you can see how wide the swath is for OCI, and you get a sense of what 20 degrees actually looks like. Then this should transition to HARP2 eventually. Stop. Okay, again, you can see that the swath roughly matches that of OCI, and the fact that it really is hyperangular. There's only a number here, but you might imagine for the red band that's completely filled in. 60 view angles is a lot. And then SPEX1, just to get a sense of where the 5 different viewing angles are positioned, and that is a much, much narrower swath than what you have for OCI and HARP2. While that starts to animate again, there's going to be something that pops up here. I often get the question about data latency. The requirement is 24 hours from collection to online for your use. We're averaging somewhere between 6, 9, or 10. So it's not direct broadcast, but within 12 hours, on average, you're going to have the data available to you from various different places, which we'll talk about in a second. Okay, so that will basically paint the globe for another 30 seconds or so, which I'll let run just so you can see how the swaths play off of each other. And one thing you will need to be aware of is that I say HARP2 is a wide swath instrument, but because it's multi-angular, the swath varies depending on what angle you're looking at. And so this is just an example of what they look like together. And in this case, all of these gaps get filled in the next day. So on a note, OCI actually can see the entire globe. It doesn't have any of these gaps in it. It will see the entire globe and paint it every day. If you're an ocean color aficionado, you know that our atmospheric correction doesn't always work at these high viewing angles, so we do tend to restrict the geometry. So this is an algorithm gap, not a inter-orbit gap. Okay, one more picture of the beautiful observatory, and just pointing out some things again that set this apart, which are going to be important to you. We've gone through why this hyperspectral universe is essential for moving the community forward. Really neat things, again, a lot to exploit in the ultraviolet. From 340 to longer wavelengths, the data look really good. I mean, they're preliminary, but they're really good. So you get a smaller spatial footprint for ultraviolet retrievals there than you do with most other instruments, like Tempo or whatever. So there is an opportunity there to do things in the ultraviolet that we've not done before. 2.2 micron bands are really useful for cloud retrievals because one is positioned at a MODIS wavelength, the other is positioned at a VIIRS wavelength. Those two positions thermodynamically for cloud retrievals don't match up. One of them is really great for ice cloud retrievals. One is really great for liquid cloud retrievals. And so while we don't have thermal bands and we're not a perfect cloud retrieval instrument system, there is a lot of continuity type work that can be done utilizing the 2.2 micron bands. And then yay, we've got polarimetry, and yay, we tilt. All right, so where are we as of roughly 6 months into the mission? Data was released to the world on 11th of April. This was 63 days into our life cycle on orbit. This included radiometry, level 1 from all 3 instruments and a heritage suite of ocean color products from OCI. So if you played around with it at all, That's what you had for most of the 178 days. We did roughly a month ago complete our first reprocessing, so you should all be looking for the tag V2. This included the first use of on-orbit calibration, and so there were some wiggles in the data, and they have started to go away. We also released terrestrial and aquatic surface reflectances, some terrestrial vegetation indices, and cloud optical properties. So unless you create your own product, and I'll talk about this in the next slide, this is roughly what's available to you. And there are release notes out there. I think it's online, but there are definitely features in the data you will have questions about. We're still learning to do everything, and we have not done a system vicarious calibration. We haven't done an absolute calibration of our shortwave infrared bands. I mentioned the two spectrographs where they overlap. The data is a little wonky. You might want to avoid it. Carina has built a really nice website that highlights all of these features that is really worth taking a look at, because if you're saying, hey, what I'm playing with doesn't look good, it might just simply be because you're using part of the spectrum where we know you shouldn't be doing something. So we'll have another reprocessing in the next, hopefully 2 or 3 months, and that'll have system vicarious calibration as well. Because maybe you will be data providers as well at some point, that we don't have real predefined deadlines on release of advanced products. We are doing it in collaboration with the PIs and the algorithm providers, and when they say we're ready and we say, yeah, you look ready, then we release things. So it's just kind of a slow burn to get data products out on the street. So here's what you have at your fingertips. I think there will be talks later today about how to get the data. It is a little bit confusing because it is different than what we used to do and what we continue to do with our other missions. We do not have the authority to release any PACE data using the Ocean Biology Processing Group Level 1 and 2, Level 2 browser. So if you've ever gone and got data from us through the GUI, you'll notice PACE data is no longer there. So all of the official data that have been blessed go through NASA's Earth Data Search, which puts data in the cloud. So we're moving that way. So if you want level 1 or 2 data, it is really just those products that I told you about, and you would go into Earth Data Cloud for that. Now, all of our test products, the ones that are unvalidated, we have the authority to put level 3 and level 4 maps online through the OBDAC and the Ocean Biology Group ecosystem. And so that's where you're going to find some of these test products, and they only come in level 3. So just know that this is available if you need reference. We'll talk about this more because obviously if you can't get the data, why are you here? So that's going to be forefront. Okay, and then if you're curious about the status of data products, there's a stoplight chart on our website. It is a laundry list of everything we're hoping to produce. If you see something that's red, you might be, ooh, I have an idea. I should write a proposal. We love that. There's documentation linked on the side. And then just kind of wrapping this up, talking about what the data look like to get you super jazzed. Well, we were able to release the data 63 days in, mostly because the radiometry from all 3 instruments is, we couldn't be happier. There's a lot of work to be done, but for a first cut, there was no reason to hold on. This is just a quick thing I had to do about day 59 to show that we were happy with the radiometry. Of course, we don't have field data yet at this point. We're not really operational, so it's simply a global map of one color, one blue, where I'm comparing OCI with VIIRS, and you can see that the patterns are pretty similar. The coverage is better with OCI, but then if you start drilling in to any particular pixel, you see that the spectra themselves really do line up. So there are features in here, that need to be nailed down. But I can honestly say for our NOAA friends here, we finally figured out how to calibrate VIIRS for you. Okay, and then just some promise, and if you have questions about this algorithm, I will direct you toward Priscilla over there. So this is just one of the examples that we used for First Light to demonstrate we do some credible retrievals of community structures. So chlorophyll here, 3 different species here as well too. Again, unvalidated, but we're trending in the right direction to be able to live up to the promise of PACE. Local to UMBC, Lorraine Reamer's group has done some really interesting work, and it's modernized since she provided this. But aerosol retrievals from OCI that are above and beyond what we've been able to do before. Specs 1 and the HARP2 team are doing really interesting things. Here's an example of something other than a particle retrieval from the Specs 1 team, getting to black carbon and sulfates and nitrates. And we even, and this surprises us because it wasn't required, but there's, Fred and others, again here at UMBC, have shown that the hyperspectral nature of OCI is going to be really valuable for terrestrial retrievals as well. So we're kind of psyched about that. Again, just to hopefully energize you to start using it. All right, I'm going to get out of here because I know we got a few minutes left, but I want to leave time for questions. Out and about in the community, just so you know where we are with that. We do have a science and application team that has been formed. Selections have been made. This will be for algorithm refinement for the most part. I hope many of you know that there's a Science of Pace call that's out in Roses now that I think NOIs are due in October and proposals are due in January, but that is for you all. Take what you learned this week and say, I have a really great idea to do science with Pace. We're not worried about the algorithms in that call. We're worried about go do something remarkable with this observatory you can't do with any other. You might care about these three because we have a validation science team out in the field and a pretty extensive post-launch airborne campaign on the West Coast, 3 sites in California in September. They're not hypothesis driven. They are simply go collect data so we can do performance assessment. But data will be made available publicly. So whatever is collected here goes into CBAS or its equivalent within 90 days. And so there's going to be a lot of data, hopefully, that you have access to from the field and from aircraft that you can start bringing into your own work. We have 2 system vicarious calibration teams. There's only one in the field right now, but again, data from the HyperNav system are readily accessible and hopefully very useful for you. We're also trying to consolidate our mailing lists, so you can find this on the front of. If you want to hear from myself and others, then join that. The website has a ton of information. I will highlight 2 things. One, that if you're curious about data characterization, like spectral responses, that's online. If you wonder why we made certain design choices, there are technical memos that describe all of that. I'll do my best to answer your questions. And then last, if you really, really are bored or can't sleep one night, there are a couple of papers out there that take those first 5 or 6 slides that I gave you, if you're interested in the history, and they outline all of those. So if that is of interest, either talk to me or read these if you have insomnia. Okay, so with that, 9:40, you can ask questions now. I'm here all week. But that's now you know everything about the past 25 years of Pace and what's available today. So probably not going to hear much from me going on other than as a bullshit meter going, hey, that's a really great science question. It's not going to work. Excellent. Okay, then I don't know what's next. I'm done. Oh God, I'm done for the week. Brilliant.